When people imagine a mission to Mars, they usually picture the journey outward, the launch, the long voyage, the landing on that silent red world. But the real problem is not getting there. The real problem is coming back. And the reason is something so simple, so unavoidable, that it almost feels cruel: energy. Rockets don't move the way cars or airplanes move. A rocket must carry everything it needs to push itself forward. It throws mass backward to move forward. That means every extra kilogram you want to move, life support, equipment, fuel, requires even more fuel to push it. And that extra fuel has mass too, which requires even more fuel. The logic loops back on itself. It's not engineering inconvenience. It's a mathematical trap built into the laws of motion. Now think about Mars. If you want to leave Mars and return to Earth, the fuel for that return trip must already be on Mars when you arrive, or you must manufacture it there. But to place that fuel on Mars, you must launch it from Earth first. And to launch that fuel from Earth, you must carry the fuel needed to push that fuel across tens of millions of kilometers of space. Every step multiplies the mass. Every layer compounds the energy demand. The rocket equation doesn't negotiate. It simply counts. People often imagine space travel like crossing an ocean. You pack what you need, sail across, and sail back. But Mars is not an ocean crossing. It's more like climbing a mountain where every step upward requires carrying the fuel for the next 1,000 steps, plus the fuel required to lift that fuel in the first place. The deeper you think about it, the more the logic tightens. Even Mars itself doesn't make things easy. Yes, its gravity is weaker than Earth's. That sounds helpful, but it still has enough gravity to demand enormous launch energy. And unlike Earth, Mars offers no infrastructure, no refueling stations, no supply chains, no repair facilities. On Earth, every launch is supported by an entire industrial civilization, factories, engineers, replacement parts, testing facilities. On Mars, you have whatever you brought and nothing more. This changes the psychological meaning of the mission. When you leave Earth for Mars, you are not simply traveling outward. You are carrying the burden of your return with you, hidden inside layers of mass, fuel, and fragile machinery. The return journey is not a separate event. It is a weight pressing on the mission from the very beginning. And here is the uncomfortable philosophical truth. Physics does not care about intention. It does not reward bravery. It does not bend for ambition. It only measures mass, distance, and energy. You can hope, you can plan, you can innovate, but you cannot argue with the numbers. So when we talk about returning from Mars, we are not talking about building a bigger rocket. We are talking about confronting a fundamental asymmetry between desire and physical law. Reaching Mars is an act of exploration. Leaving Mars is an act of escape. An escape demands preparation on a scale that borders on building a world before you can leave it. And that is the quiet reality hidden behind the dream. The farther we go, the more the universe asks us a simple question, not whether we are brave enough to arrive, but whether we were wise enough to prepare for the cost of coming home. And then there is something even more unforgiving than fuel: time. Not the kind of time we measure casually with clocks and calendars, but orbital time, celestial timing. The kind that doesn't care whether your systems are functioning, whether your crew is exhausted, or whether something small has already begun to fail. When astronauts travel to Mars, they cannot simply leave whenever they choose. Earth and Mars are constantly moving in their own orbits around the Sun. The distance between them stretches and shrinks in a slow cosmic rhythm. The alignment that allows an efficient return trip happens only about once every 26 months. Miss that window, or be unable to launch when it opens, and you wait, not days, not weeks, years. Now imagine what that really means in practice. You are living on a planet that was never meant to support you. The air cannot be breathed. The temperature can freeze machinery into brittleness. Dust storms can cover solar panels for weeks. Radiation constantly penetrates the thin atmosphere, quietly damaging electronics and human tissue alike. Every system keeping you alive is artificial. Oxygen production, water recycling, temperature control, pressure regulation. None of these systems can fail, not once, not even briefly. On Earth, when something breaks, we repair it. We replace parts, we call experts. We rely on supply chains so vast we rarely notice them. But on Mars, repair is improvisation. Every component has a limited lifespan. Every seal weakens. Every circuit ages. You are not maintaining a habitat, you are delaying entropy. And time magnifies everything. A mission lasting months is difficult. A mission lasting years is something else entirely. Humans are not designed for prolonged isolation in confined, high-risk environments. Psychological strain becomes as real as mechanical strain. The same narrow walls, the same small group of faces, the same awareness that beyond those walls is immediate death. Patience is no longer a virtue, it is a survival requirement. Even if every system works as designed, degradation is unavoidable. Filters clog, metals fatigue, software accumulates errors, microscopic damage compounds silently. The longer you wait for the return window, the more the probability of failure slowly rises, not dramatically, not suddenly, but steadily. Like a quiet leak in a sealed chamber, this is the part many people underestimate. The return journey is not just a matter of having enough fuel. It requires something far more fragile, uninterrupted survival across an extended, unforgiving stretch of time. One failed oxygen valve, one contaminated water system, one structural fracture caused by thermal stress. Any single failure at the wrong moment eliminates the possibility of departure entirely. This is where the deeper realism emerges, something often emphasized by Richard Feynman in his relentless respect for nature's indifference. Complex systems do not fail because of dramatic catastrophes. They fail because small problems accumulate faster than they can be corrected. Mars does not need to destroy a mission violently. It only needs to wait patiently while things slowly wear down. And so survival itself becomes the gatekeeper of return. You are not simply waiting for the planets to align. You are maintaining perfection in an environment that constantly erodes it. Time is no longer a neutral backdrop. Time becomes pressure. Time becomes risk. Time becomes the quiet force deciding whether leaving Mars remains possible at all. The profound realization is this. Reaching Mars demands engineering brilliance, but surviving long enough to leave demands something even harder, sustained perfection in a world designed to dismantle it. And that leaves us with a sobering reflection. In deep space, survival is not measured by how far you travel, but by how long you can prevent the universe from slowly reclaiming what does not belong. There, people often respond to all these challenges with a reassuring idea. We won't need to carry all the fuel from Earth, we'll just make it on Mars. It sounds elegant, logical, even inevitable. Mars has carbon dioxide in its atmosphere. There is frozen water in the soil. With the right chemical processes, you can produce methane and oxygen rocket fuel. In principle, the planet itself becomes your refueling station. But notice the phrase we quietly depend on there, in principle. Turning a hostile planet into a functioning chemical factory is not a simple technical step. It is the creation of an entire industrial process in an environment where industry has never existed. On Earth, fuel production depends on massive infrastructure, mining, refining, manufacturing, power generation, maintenance systems, trained personnel, spare parts, quality control. All of that complexity is normally distributed across entire nations. On Mars, it must exist in miniature, self-contained, and perfectly reliable. And reliability here is not a convenience, it is the condition for survival. Imagine the chain of requirements. You must extract water from frozen ground. That requires drilling systems that function in extreme cold and low pressure. You must purify that water. You must generate large amounts of electrical power to split molecules and drive chemical reactions. That power system must survive dust accumulation, radiation exposure, and mechanical fatigue. Then the fuel production equipment must operate continuously, precisely, and without contamination. Valves must seal, catalysts must remain stable, sensors must remain accurate. Storage tanks must hold volatile fuel safely for months or years. Every step must succeed, not mostly succeed, completely succeed, and if something breaks, on Earth, a malfunction triggers a supply request. A replacement part is manufactured, shipped, installed. Engineers analyze the failure and adjust the design. But on Mars there is no warehouse, no express delivery, no specialized technician arriving tomorrow. You have only what you brought, and what you can improvise from limited materials under extreme constraints. This is the illusion hidden inside the idea of self-sufficiency. We imagine independence as freedom. But in an environment like Mars, self-sufficiency is actually total dependence. Dependence on systems that cannot fail because nothing exists beyond them to help you recover. This is where the philosophical weight becomes clear. We often treat technology as if it naturally trends toward robustness, as if complexity automatically becomes manageable with enough intelligence. But nature does not reward complexity. Nature tests it continuously, relentlessly. Every additional process, every additional component, every additional interaction is another opportunity for failure to emerge. This is something Richard Feynman insisted on with unusual clarity. Reality does not respond to what we intend, it responds to what actually works. And complex systems in unforgiving environments reveal the difference very quickly. So when we say we will manufacture fuel on Mars, what we are really saying is that we will construct a perfectly functioning industrial ecosystem, isolated from all external support, operating for years without interruption in conditions that constantly degrade materials and strain precision, not because it would be efficient, but because without it, leaving becomes impossible. And this changes how we should think about exploration itself. Visiting Mars is not like planting a flag. It is not even like building a base. It is closer to planting the seed of an entire civilization, because anything less may not be stable enough to bring you home. That is the quiet truth beneath the promise of living off the land. On Mars, self-sufficiency is not empowerment. It is the most fragile form of dependence we have ever attempted to engineer. And perhaps that is the lesson worth carrying with us. Survival does not belong to those who can build remarkable machines, but to those who understand how easily remarkable machines can fail when nothing exists to catch them. And beneath all of these technical barriers, the fuel, the timing, the fragile machinery, there is something even more fundamental shaping the reality of Mars exploration, something quieter, but far more decisive, the fact that physics does not negotiate with human hope. Human progress is built on a powerful habit of mind. When we encounter a limitation, we assume it is temporary. Mountains were once barriers, then we climbed them. Oceans separated continents, then we crossed them. The sky itself seemed unreachable until we learned to fly. Over and over again, history has rewarded the belief that ingenuity eventually dissolves every obstacle. So, naturally, when we look at Mars, we carry the same assumption. If returning is difficult today, we imagine it will simply become easier tomorrow. Better engines, smarter systems, more efficient chemistry, stronger materials. The story we tell ourselves is that technology is a rising tide, and every problem is just a matter of time. But the universe does not operate on historical optimism. It operates on physical law. There are limits that do not soften with effort. Energy requirements that cannot be negotiated downward. Biological tolerances that cannot be stretched indefinitely. Materials that will always weaken under stress, radiation, and time. These are not engineering problems waiting for clever solutions. They are boundary conditions written into the structure of reality itself. Mars is not merely distant. It is fundamentally indifferent. It does not resist us with intention. It does not oppose us with hostility. It simply exists in a state that is incompatible with human life, and maintaining compatibility requires continuous, precise, and immense effort. Every breath must be manufactured. Every drop of water must be recovered. Every degree of temperature must be controlled. Every gram of fuel must be planned years in advance. This creates a profound psychological tension. Exploration is usually framed as expansion, moving outward, claiming new ground, extending presence. But Mars reverses that narrative. The farther we go, the more tightly constrained we become. The environment does not open possibilities, it narrows them. Survival becomes a constant negotiation with forces that never relax their pressure, and that leads to a deeper philosophical realization. Perhaps the greatest challenge of Mars is not technological at all. It is conceptual. We must confront the possibility that reaching a place does not mean we can truly inhabit it. That access is not the same as belonging. That arrival does not guarantee return. This is the kind of intellectual honesty that Richard Feynman championed relentlessly, the refusal to confuse what we want to be true with what reality allows to be true. Nature is not impressed by ambition. It is not persuaded by vision. It responds only to what is physically sustainable. And when we follow that logic to its conclusion, a striking picture emerges. A truly reliable return from Mars may not depend on a single mission at all. It may require something far larger, an established industrial presence, redundant systems, long-term resource networks, continuous production capacity. In other words, not a visit, but the early foundations of a second world built by humans. Until then, every journey outward carries an asymmetry. Going is an act of courage. Coming back is an act of infrastructure. And that distinction matters because it forces us to ask a different kind of question. Not can we reach Mars, but what must we become as a civilization to leave it safely? That is the real warning hidden inside the dream of interplanetary travel. The universe does not challenge our ability to go farther. It challenges our willingness to accept the cost of surviving where we do not naturally belong. And perhaps the most important reflection is this: the future will not be shaped by how boldly we chase distant worlds, but by how honestly we understand the limits that wait for us when we arrive.